All right, once again, we're going to be talking about these silicate minerals, and silicate minerals are the most important group of minerals that we find at the Earth's surface. Remember back to Sial, oxygen and silicon make up, I don't know, 75% of the material we find at the Earth's surface by mass. So it's not really surprising that they would come together to form what we call a silicate mineral, or silicon, oxygen, and then the X just means that we're going to vary the number of oxygens that we use. All right, now hopefully you have watched the PowerPoint and you've done all the preliminary work. If you remember, the most simple form of a silicate mineral is an isolated tetrahedron. Now, my example is olivine, okay? That's my mineral example. And olivine is olive green. Now, it's in this little jar, and I've got little pieces of it, and it looks like little green glass, okay? And if you remember, this is the highest temperature mineral. And the only way that those isolated tetrahedrons are going to come together is with a whole lot of iron and magnesium. Okay, and we also said that this is the highest temperature. What I'm writing here over on the sides are the relationships. You guys are not going to have to memorize a bunch of numbers, 1300 degrees Celsius, just high, and then we're going to find out that this is the lower temperature range down here. Okay, and so we'll do something like this, that we go from high to low temperature. All right, so here's where we're using iron and magnesium to glue this together. And again, olivine is olive green. The next one, if we cool this down just a little bit, what we can do is, of the 4 oxygens in the isolated tetrahedron, 1 will be shared, and we'll make what was called a single chain. Okay, now single chains make up a mineral group. The big group are called the pyroxenes. Okay, and if you're in lab, you are looking specifically at augite. Okay, and here's an example of augite. All right, you can see that this was green. This is kind of blackish green. Now, you guys, you only have to know one of those words. You don't have to know both. But if you are in lab, you will learn the mineral augite. And augite's just one member of the pyroxene group. All right, so we're still using iron and magnesium. We are only sharing 1 oxygen. We still have a net negative charge, and we still need cations, or positively charged ions, to hold them together. And that's what alpha-fecunacmig is, and at high temperatures, it's iron and magnesium. All right, now if we cool it down just a little bit more, what's going to happen is we're going to start to share every other. We're going to have 2 chains hanging, and across the chains, we're going to share an oxygen. And so this is called a double chain. Now, once again, we're going to have a big group, and the big group are called the amphiboles. And if you're in lab, you will be looking at a beautiful mineral called hornblende. And here's hornblende. Hornblende is really important. Now, you guys, we're going to talk about cleavage, or way a mineral breaks. And if you look where my fingers are, this is the small angle. Okay, and then you can see here that there's a big angle. And so if you're looking at an example of this, you can always find this little 60-degree angle. Here's the 120-degree angle, and identify it. And it's black, it's shiny, it's needly, it's really pretty. Now, in the amphibole group is a really nasty relative to hornblende. Okay, I love hornblende. Hornblende is not dangerous. And that's asbestos. Everybody here probably knows a little bit about asbestos, and you know you don't want to be around it. Hornblende's a safe version. All right, it's black. We're going to find out that things that contain iron and magnesium tend to be dark in color or strongly colored. We are still using iron and magnesiums. Okay, until we're sharing every single oxygen, we are going to have a net negative charge. All right, down here we have what's called the sheet silicates. If we have a bunch of double chains and then they share oxygens between them, we'll make these great big sheets. Now you'll notice this box over here is broken into 2, and it's really important. Something happens right here. Now, of the sheet ones, we have 2 samples, biotite and muscovite. And you guys, they are similar, but they're also different. They are sheets. And if you look at this, this is not man-made, you guys. This you can find out in nature. Check that out. I'm pulling it apart. And so the sheet part is across here, the strong covalent bonds, and the weak ionic bonds are what's holding this together. Now, here's the white version. That's muscovite. And here's B, black, biotite. Same thing here. Okay, we're pulling it apart. Those are weak ionic bonds. Okay, now with the biotite, this is the end of iron and magnesium. We are gluing it together with iron and magnesium, and that's what gives it the black appearance. But we just ran out of iron and magnesium, and so to hold the sheets, and the sheets are exactly the same. The only difference is kind of the jelly or the positively charged ion holding them together. This is going to be aluminum and potassium holding it together. Okay, so of alpha-fecunacmig, we've just used up Phe and Mig, and now we're using Al and K right here. All right, so we are now out of the minerals that contain iron and magnesium. Now, another relationship I want to write up here is the fact that if you contain metals like iron and magnesium, you're more dense, right? Okay, and then we're going to go down. We contain no iron and magnesium once we're below this, and this is my less dense. Okay, something else I needed to mention is olivine is SiO4. There's more here with the iron and magnesium. Eventually, we're going to come down here to the ultimate silicate, which is quartz. And so we're going to go to SiO2. And when we're at SiO2, we don't need any positively charged ions. And so it's kind of a silicon to oxygen ratio, 1 to 4. And here's a silicon to oxygen ratio of 1 to 2. All right, that last box, though, this is something kind of weird. It's not the last box, it's the second to last. Okay, with a framework, we are sharing all oxygens, but something really weird happens with this group called the feldspars. And I brought 2 examples of the feldspars. If you guys are in lab, you'll learn the difference. One of them, this is going to be my higher temperature one and my lower temperature one. And the feldspars, yeah, they're frameworks, but some of the silicons have been substituted for aluminum. Silicon is a +4 charge, aluminum is a +3 charge. Okay, and so what's going to go on here is that we're going to have to be glued together now because we still have a net negative charge. And this version right here is glued together with calcium and sodium, and this version right here, it's called potassium feldspar because it's glued together with potassium. So OSI, Al, Phe, Ca, Nac, Mig. We've just used up all of those cations or positively charged ions to glue it up. And if you look down here, relate the temperatures, higher, lower, oxygen to silicon ratios. Okay, we got that here. Amounts of iron and magnesium, only olivine, augite, hornblende, and biotite have iron and magnesium. Below that we have none. And then the density. Obviously, if you contain iron and magnesium, you are more dense. These contain none. And in fact, quartz is a very low density mineral because all that's in there, again, SiO2. And I don't think I showed you the quartz crystal, but here's a big piece of quartz. And I think everybody here knows what quartz looks like.